Comparative analysis of performance characteristics of a compression ignition engine fueled with Cymbopogon oil methyl ester and diesel blends with base engine and coated engine. Abstract: in a standard internal combustion engine, a large amount of heat energy is being wasted through the cooling and exhaust systems. So, to minimize these losses, one advanced technology for coating applications grows rapidly. Hence, to improve engine performance and fuel economy, one or more parts of the combustion chamber such as piston crown, inlet valves, exhaust valves, and cylinder head are getting coated with ceramic materials without changing the original dimensions. The present work deals with the performance characteristics of a single-cylinder diesel engine with an eddy current dynamometer loading fueled with Cymbopogon, lemongrass, oil methyl ester, CME, when the piston crown was coated with yttria stabilized zirconia of thickness 350 microns equal to 0.35 mm of thickness using plasma spray coating technique. Test samples were prepared and designated as CME10D90, B10, CME20D80, B20, and CME30D70, B30. Tests were conducted and comparison is done with the performance results of coated and uncoated piston named as the base engine and coated engine respectively. Finally, the experimental results revealed that, at full load condition, the BSFC, BTE, and TFC of the blend CME10D90, B10, with the coated engine were improved by 3.61%, 4.05%, and 3.91% respectively compared to that of the base engine. Keywords: Cymbopogon methyl ester, yttria stabilized zirconia, ceramic coating, plasma spray coating technique, engine performance characteristics, brake thermal efficiency, brake specific fuel consumption, total fuel consumption. Introduction. Diesel engines are playing a very dominating role in the fields of transportation and power generation. From the past few years we are witnessing an energy crisis, especially in the sector of the automobile industry due to the unavailability of petroleum products according to the demand, and also escalating oil prices. Not only due to the demand and supply of petroleum, moreover the environmental concerns, there is much need for an alternative to mineral diesel. All such reasons made the researchers to focus their research to find a suitable solution to fix this issue. Most of the researchers have suggested several types of biofuels extracted from various sources of feedstocks such as edible seeds, non-edible edible seeds, and biomass etc., and now biodiesel from algae is getting more focus among all. Though the biodiesel has the potential to replace the conventional diesel fuel, it makes a significant impact on diesel engine combustion due to lower combustion temperature, lower calorific value, higher viscosity, and the transesterification reactant also influences the engine performance and emissions. Hence, in order to make biodiesel more attractive towards performance and emission features, the researchers concentrated to improve the biodiesel efficiency. Different performance enhancement techniques such as changing injection pressures and timings, different compression ratios, adding nano-fuel additives, coating the piston crown and valves, exhaust gas recirculation, water emulsion, and selective catalytic converters, etc., are being used. 1. The present literature review reports the various research conducted on compression ignition engines using different kinds of biodiesel and pure diesel blends and their related issues under various techniques. Gunputty et al., 2011, investigated the performance, emission, and combustion parameters of a compression ignition engine using Jatropha biodiesel at various injection timings, and found that on advanced injection timing, the performance, combustion, and emission was better than the rated timing too. Nambaya Charyulu Tatikonda, P. Navanchandran, 2019, investigated the behavior of a compression ignition engine under the influence of microalgae methyl ester at various proportions with pure diesel at the range of 10 to 30% and found that the blend B30, 30% microalgae methyl ester plus 70% pure diesel, produced better performance and emission results compared to that of fossil diesel at standard operating parameters. 3. Avinash Kumar Agarwal et al., 2010, has studied the performance and emission characteristics of single-cylinder diesel engine when it was fueled with Karanja biodiesel, and it was reported that they have obtained better spray and atomization characteristics when biodiesel was preheated for. Deepak Agarwal and Avinash Kumar Agarwal, 2007, claims that, while the single-cylinder 4-stroke diesel engine operating by Jatropha oil preheated blends, the performance and emission parameters were found very close pure diesel for lower blend concentrations, and for higher blend concentrations they observed to be marginally inferior. 5. Nambaya, Charyulu, Tatikonda, and P. Navanchandran, 2019, have reported the impact of injection pressure on the performance and emission characteristics of a direct injection diesel engine driven with microalgae methyl ester at 30%, and stated that no significant improvement was found with modified injection pressures. 6. Agarwal AK et al., 2001, reported that 20% blend of biodiesel gave the best performance amongst all blends. It gave net advantage of 2.5% in peak thermal efficiency, and there was substantial reduction in smoke opacity values, and also, they have stated that biodiesel can be used as an alternative, environment-friendly fuel in existing diesel engines without substantial hardware modification. 7. G. Vinod and P. Balaguru, 2019, have studied the performance characteristics of lemongrass oil in a single-cylinder diesel engine at various injection pressures, and found that the blend B20 has produced optimum values of specific fuel consumption, brake thermal efficiency, and emission parameters at modified injection pressure of 240 bar 8. T. Nambaya, Charyulu et al., 2020, have studied the impact of Artocarpus heterophilus methyl ester on the behavior of a compression ignition engine, and stated that 30% of blend explored better results towards performance and emission than that of pure diesel. 9. Ashok Kumar Jalasutram et al., 2019, stated as per the outcomes of the experiment conducted on a single-cylinder direct injection diesel engine with lemongrass biodiesel and pure diesel blends, that the brake thermal efficiency has found to be higher for B50, and specific fuel consumption is increased for the lemongrass biodiesel blends. 10. Venugopal v. et al., 2014, have reported that lemongrass biodiesel and pure diesel blends at 30:70 ratio has registered improved values of brake-specific fuel consumption and brake thermal efficiency as far as performance characteristics are concerned. 11. Nambaya, Charyulu, Tatikonda and P. Navanchandran, 2019, reported the experimental results related to the investigation for the performance and emission characteristics of a single-cylinder direct injection diesel engine fueled with Methyl Charazopoda methyl ester and pure diesel blends, that reveals as far as performance characteristics are concerned B20 performed well, whereas emission parameters are concerned B30 exhibited improved results. 12. Vinay Kumar D. and Ravi Kumar P. 2017, have reviewed the effect of insulation with ceramic materials on the performance, combustion, and emission characteristics of a diesel engine and discussed the reasons for each deviation. 13. Hussein Aden, 2013, reported his experimental results from zirconium oxide-coated engine with cottonseed, sunflower pure vegetable oils blended with diesel, and stated that engine power, torque, and fuel consumption were improved, emissions were decreased with coated engine. 14. Abedin M.J.et al., 2014, have investigated the contradictory results of several researches on low-heat rejection engines and said that more investigation with improved engine modification and design are required to explore the potentiality of LHR engine. 15. Selman Aden et al., 2015, experimentally reported the influence of thermal barrier coating on engine performance and emissions and claimed that by coating process, partial increases were observed in power and engine noise, while partial decrease were found in brake-specific fuel consumption, besides partial reductions were seen in emissions except nitrogen oxide. 16. V. Karthikeyan et al., 2016, reported their experimental results on diesel engine coated with partially stabilized zirconia powered with various non-edible oils at 20:80 ratio with diesel. The report says, higher thermal efficiency, lower brake-specific fuel consumption along with lower emissions were observed. 17. V. Karthikeyan, 2017, has tested the diesel engine coated with partially stabilized zirconia running on orange oil methyl ester at 20% blend with diesel and observed that increase in brake thermal efficiency, reduction in brake-specific fuel consumption and emissions. 18. M. Selvamiti al. 2018, experimented on single-cylinder diesel engine coated with yttria stabilized zirconia and found increment in brake thermal efficiency and reduction in brake-specific fuel consumption, as well as in emissions. Increment was observed in nitrogen oxide. 19. Banaparmath and Tiwari, 2008, have studied the performance and emission characteristics of a thermal barrier-coated, zirconia, diesel engine at constant speed with hong oil and its methyl ester with optimized injection timing as 190 ca/btdc, and at full load it has been reported that, the BTE and BSFC were improved as that of base engine. 20. Hanbi Hazer, 2009, who studied the performance characteristics of a ceramic-coated, MgO002, diesel engine using canola methyl ester blends at different speeds at full load. It has been reported that the brake thermal efficiency of the engine is increased about 3.5% and the BSFC decreases 8% for alternative fuels. 21. The above studies reveal that the diesel biodiesel blends can be used as alternative fuels for diesel engines with and without engine modifications such as modifying injection pressure, injection temperature, preheating of fuel and air, doping with nanoparticles, and thermal barrier coatings, etc. Recent research has shown that the use of diesel biodiesel blends can substantially increase engine performance and reduce emissions by doping the fuel or coating inside the combustion chamber. They had also suggested some alternative fuels which are friendly to the atmosphere. Therefore, in the present study Cymbopogon oil, lemongrass oil, methyl ester was chosen as a fuel, because less research was observed with this biodiesel in modified engine, and yttria stabilized zirconia was chosen as thermal barrier coating for piston crown as this combination was not found so far in the past research. Hence the present work has found the research gap in this area, and it reveals the comparison between the base engine and coated engine for the performance characteristics when the compression ignition engine was run with the blends of Cymbopogon oil methyl ester and mineral diesel in the blending ratios 10:90, 20:80 and 30:70 respectively. 2 Materials and methods. A. Preparation of biodiesel. Cymbopogon crude oil was purchased from Lemongrass oil extraction plant, which is located at Cymbopogon near Tiruviru, Andhra Pradesh state. The Cymbopogon crude oil is subjected to transesterification in our laboratory as follows. Crude Cymbopogon oil is measured 1000 ml and is taken in a round bottom flask. 12 grams of potassium hydroxide as an alkaline catalyst, KOH, is weighed and 250 ml of methyl alcohol is taken in a beaker. First of all, KOH is mixed with the alcohol and it is stirred until they are properly dissolved with each other. Then the crude Cymbopogon oil already taken in a round bottom flask is stirred with a magnetic stirrer and simultaneously heated with the help of a heating coil. The speed of the stirrer should be minimum, approximately 110 rpm, and when the temperature of the crude Cymbopogon oil reaches 600 C, the KOH alcohol solution is poured into the crude Cymbopogon oil container and the container is closed with airtight. Now the solution is stirred at high speeds, approximately 700 to 800 rpm. Care must be taken that the temperature does not exceed 600 C as the methanol evaporates at a temperature higher than 600 C. Also the KOH alcohol solution mixes with the crude Cymbopogon oil only at 600 C. To prevent the methanol loss during a reaction, a water-cooled condenser was used to condensate the vapors and reflux it back to the reactor. After stirring the oil KOH alcohol solution at 600 C for 2 hours, the solution is transferred to a separating funnel, and then it was allowed to cool overnight without stirring. After complete cooling, 2 layers were found. The bottom layer consisted of glycerol and the top layer was the biodiesel, i.e., Cymbopogon methyl ester. The biodiesel is washed with water, preferably distilled water, repeatedly till ensuring that no soap content is present in the biodiesel. Now this biodiesel is heated at 1000 C for a while to vaporize the water content in it. Finally, the resulting product is the Cymbopogon biodiesel, which readies for use. The transesterification process was depicted in the figure 1b. Preparation of biodiesel diesel blends. Cymbopogon methyl ester and pure diesel blends were prepared for 500 ml quantity, firstly by mixing 50 ml of Cymbopogon methyl ester into 450 ml of pure diesel with the aid of magnetic stirrer for 5 to 10 minutes, and it was labeled as CME10D90 briefly B10, and same procedure was followed to prepare another two blends and were labeled as CME20D80 briefly B20, and CME30D70 briefly B30. The test samples were shown in the figure 2, and the corresponding physicochemical properties of fuel samples CME, B10, B20, and B30 were shown in the table 1. C. Preparation of coated piston. In the present investigation, the piston crown was coated with yttria stabilized zirconia of 0.35 mm thickness to achieve semi-low heat rejection, LHR, engine which withstands higher temperature in the combustion chamber that promotes the combustion. The coating of the piston crown was done at Spraymit Surface Technologies, Private Limited, Bangalore. The objective of the present study is to improve the performance of a diesel engine with ZrO2 coated piston using Cymbopogon methyl ester blends with various ratios ranging from 10% to 30% at different load conditions. The measured values are analyzed and compared with the base engine running with the same blends and pure diesel. The piston before coating and after coating were shown in the figure 3. D. Experimental setup. The present study was carried out to find the influence of Cymbopogon methyl ester blends such as CME10D90, B10, CME20D80, B20, and CME30D70, B30, on the performance of a direct injection compression ignition diesel engine. The engine selected for this investigation is Kirloskar-made single-cylinder, 4-stroke, direct injection, water-cooled diesel engine of 5.2 kW brake power at constant speed of 1500 rpm 3,6,12. The specifications of the engine are depicted in Table 2. This engine was associated with eddy current dynamometer with control systems. The engine is provided with crank angle sensor, thermocouples to measure the temperature of exhaust gas, and water. The photographic view of experimental setup is viewed in Figure 4. E. Experimental procedure. Firstly, allowed the engine to run with pure diesel at rated speed, 1500 rpm, for a few minutes, and then vary the load from 0 to full load in steps, 0, 25%, 50%, 75%, and 100%, noted down the readings of performance parameters at each load. Secondly, powered the engine with B10, B20, and B30 and experiment was repeated, and all the performance-related readings were taken, and thirdly, piston of base engine was replaced with ZrO2 coated piston and run the engine again with the same test samples such as B10, B20, and B30, recorded all the necessary readings as above. Finally, the experimental results were analyzed and comparison was made between base engine data and coated engine data along with pure diesel data. F. Formulae to be used. Brake power of the engine is given by where W equals load on the engine, in kg. N equals speed of the engine, in rpm. Rm equals radius of dynamometer arm length in m. Mass of fuel consumption is given by where Q equals volume of fuel consumed equals T equals time taken for 10 cubic centimeters of fuel consumption SEC. Brake specific fuel consumption is given by brake thermal efficiency is given by where C.V equals calorific value of the fuel, kJ/kg. Total fuel consumption is given by 3 results and discussion. Figure 5 represents the relation between the brake power, BP, and brake-specific fuel consumption, BSFC, of all the test samples. It is evident from the graph that, for all the test fuels the BSFC decreased with increased brake power. Generally, Brake-specific fuel consumption is the measure of how the supplied fuel energy to the engine is converted into brake power, and it can be defined as the amount of fuel consumed in unit time for generating kW power. The experimental result revealed that the BSFC of test fuels operated with coated engine was improved compared to pure diesel and base engine. Decrease in BSFC is due to the reduction in the fuel consumption and improved energy conversion rate at all loading conditions in the coated engine. This may be due to the increased temperature of the combustion chamber walls, which increase the temperature of the fuel issued from the heated fuel injecting nozzle, resulting in the reduced fuel viscosity and better combustion of the fuel. At maximum load condition, CME10D90, B10, with coated engine registered lowest BSFC amongst all, and it was improved by 5.88% compared to pure diesel and by 3.61% compared to base engine data. Figure 6 shows the variation of brake thermal efficiency, BTE, with brake power, BP, for all the test fuels. It can be noticed from the experimental results that the BTE of all the test samples under coated engine was higher than that of base engine at all load conditions. This is due to the fact that the thermal resistance of the piston crown, which cannot allow the heat energy to coolant, thereby reducing the fuel consumption for the same amount of power output. It can be observed that, at maximum load condition, the BTE of CME10D90, B10, with coated engine is higher than that of pure diesel and base engine data. At full load condition, diesel has recorded 33.4% of BTE, CME10D90, B10, with base engine has recorded 34.57% of BTE, and with coated engine has recorded 35.97% BTE. Therefore, for coated engine the BTE of CME10D90, B10, was increased by 7.69% compared to pure diesel and by 4.05% compared to base engine data. Figure 7 depicts the variation of total fuel consumption in kg/hr, TFC, with brake power for all test samples. TFC is used to measure the quantity of fuel consumed by the engine per unit time while the engine producing a certain amount of power. It was revealed from the results that the TFC increases with increase in brake power, but the values recorded for coated engines shown lower than that base engine and pure diesel. This may due to the rise in temperature inside the combustion chamber with thermally partial insulation. Then engine requires less amount of fuel to produce same amount of power when it was not insulated. Finally, it was shown at full load condition that the TFC of CME10D90, B10, with coated engine was improved by 3.91% compared to CME10D90, B10, with base engine, and by 6.12% compared to pure diesel. For conclusions. The performance characteristics of compression ignition engine powered with conventional diesel, and biodiesel blend were investigated with and without piston coating. The conclusions of this investigation at full load condition are as follows. In general, the brake-specific fuel consumption decreases with increase in load on the engine. Among all the blends, CME10D90, B10, with coated engine registered lowest BSFC amongst all, and it was improved by 5.88% compared to pure diesel and by 3.61% compared to base engine data. Diesel has recorded 33.4% of BTE, CME10D90, B10, with base engine has recorded 34.57% of BTE, and with coated engine has recorded 35.97% BTE. Therefore, for coated engine the BTE of CME10D90, B10, was increased by 7.69% compared to pure diesel and by 4.05% compared to base engine data. Among all the blends, CME10D90, B10, with base engine has registered 76.11%, CME10D90 with coated engine has recorded 76.45%, and diesel has recorded 75.44%. Therefore, finally the mechanical efficiency of CME10D90, B10, with coated engine was merely increased by 0.45% compared to base engine data, and slightly increased by 1.34% compared to pure diesel. The TFC of CME10D90, B10, with coated engine was improved by 3.91% compared to CME10D90, B10, with base engine and by 6.12% compared to pure diesel. The volumetric efficiency of CME10D90, B10, with coated engine is lower than that of CME10D90, B10, with base engine by 1.2% and decreased by 1.33% compared to pure diesel. From the above conclusions it can be noticed that, as far as the performance parameters such as BSFC, BTE, mechanical efficiency, and TFC, are concerned, out of all the blends CME10D90, B10, with coated piston has showed better results and it was reported as the optimum blend with coated engine. In the future, this experimentation can be extended to find out the emission and combustion characteristics of the same engine with and without piston coating when it is fueled with the same blends.